what I want to talk about, though, is not just grease analysis, but really something that we spend more time thinking about, and that is condition monitoring, right? So really today, I'm going to look at the differentiation between what has typically been done for grease analysis in the past and what we're doing today, and then we'll examine that through a series of case studies from grease samples. So traditionally, grease testing has really been more about assessing or predicting grease performance in a given application, right? And I'm just going to pull up the screen here. Hang on. I don't like talking to a PowerPoint. I'd rather talk to people's faces. So the testing that was designed was really developed to look at how grease was expected to perform in a given application, a bearing or a bowl gear or something. So a lot of that type of testing was done by oil companies or very specialized labs, right? There's not a lot of the commercial type of labs that were doing grease testing in years past. We're looking at things like bleed resistance or corrosion resistance in a grease, or its ability to act in an extreme pressure environment, or anti-wear characteristics. So we were doing things like tribological testing, 4-ball wear scar, that kind of stuff. We were looking at its oxidation resistance, dropping points to determine if it was going to be suitable for use in our maybe a high temperature application. Things to assess the grease's life, shear stability, how is it going to react to the environment it's in and being worked, is it going to lose its consistency or increase consistency, and things specifically like water resistance. Was it going to be suitable in a high water application, or was it not? Even low temperature operation, pumpability, that sort of thing. If we have a distributed grease system, is the grease going to get to where we expect it? So this type of testing, as I said, was really designed for looking at how we anticipated grease was going to perform. We could test 3 different greases for our given application and see which one of them was more likely to be a better grease and use that grease. And more to that, the NLGI has begun to develop this GCLB specification, and they continue to work on that. So they're looking at GC, or the more automotive type greases, and the LB or industrial type greases. And they came up with some what they call the HPM core characteristics of those greases. So tests you would do to rate every grease out there, and then develop categories for other types of properties we want our grease to have. Things like water resistance or corrosion resistance, high load, or low temp operation. But today, what I'm going to speak about, though, is the condition monitoring side of this. So what we're doing now as a laboratory is, our customers out there have been doing oil analysis for 50 years, right? And it wasn't uncommon for them to send in the odd grease sample and ask us to do some sort of analysis. And initially, we weren't doing or offering that type of thing. But over the years, we've added a number of tests and developed some routine tests that we do in the laboratory now that are really designed to work the same as when we do an oil analysis program. So we're not trying to assess greases for their anticipated performance. We're looking at greases in operation and assessing the condition of that equipment. We're looking for contamination. We're looking at the grease's condition for continued use. And a lot of these end up being more root cause things. So typically the grease samples that we receive have more to do with, hey, I've got a problem with this, I'm losing bearings, or I'm very concerned because this is a very critical piece of equipment and I want to know what the condition is. So as a result of that, we have a test program that's a lot more streamlined and looks very similar to what we would do for condition monitoring of oil samples. Now, in terms, I'm just going to back up a minute and talk a little bit about greases themselves. You know, greases are obviously an oil that is held in place by a thickener. And just like any other oil that's out there, those oils are formulated for specific applications. And grease oil chemistry is very similar to standard oil chemistry. So we can have additives in there that form as little as 0.1% of that finished grease right up to 10%. So we definitely have antioxidants in all our grease lubricants. We have, in some cases, corrosion inhibitors. In some greases, like EP greases, extreme pressure agents. Some of the differences are things like tackiness agents that are used to ensure that greases stay in place. Well, some oils as well will use solid lubricants, and greases are no exception. There are certain solid lubricants like molybdisulfide that can be blended into grease formulations to provide a solid lubricant in the place when we have a sort of application where we may not have a fluid film. And then, unlike oils, coloring agents are employed in greases as well. I'm going to talk a little bit about that in a minute. So the primary difference between an oil and a grease, of course, is the thickener. And here I'm focusing on soaps. So we can have non-soap type thickeners for greases, things like bentonite clay or mica. But 90% of the greases out there today use a soap. And they call it a soap because it's made with a saponification process. It's no different than soap you use for personal hygiene. Soaps are made by combining a fatty acid with a hydroxide and forming soap and water. In the case of lubricating oils, though, the difference is that these fatty acids are high molecular weight stearic acids or hydroxystearic acids. And the hydroxides them are metal hydroxides. So we're combining them with something like a lithium hydroxide or calcium or sodium. And that's what provides the type of thickener we have. So we refer to these as calcium greases or lithium complex greases. So you can form simple soaps, which are that fatty acid plus a metal hydroxide, like a lithium soap. You can have a mixed soap. So in some cases, you may have one or more metal hydroxides in the thickener, like a calcium lithium soap. And then you can have complex soaps where we're combining a fatty acid with more of a short chain complexing acid and a metal hydroxide to form that soap or the thickener that the lube is blended into. And of course,
all we're talking about here is features. What about the benefits?
Who's that? Anyway, so the point of a grease itself is that the thickener is there to keep that lubricant in place. And so we apply the grease to a bearing and it's not going to move out of there, and then it's going to use the lubricant, is going to come out of the grease and do the actual job of lubrication. So just quickly, in terms of the types of greases we see out there in the marketplace, the predominant number of greases, if you add up lithium and lithium complex greases out there, they represent close to 60% of the entire market in North America. Calcium greases making a follow-up 15%, polyurea, and then aluminum, sodium greases, and others making up the rest of the percentage. So a great deal of greases we see today are soap-based. Not unlike lubricants, the viscosity is the most important property of a lubricant. When it comes to greases, probably one of the most important properties is its consistency or its NLGI grade. Now, traditionally, this is the sort of test that you would send off to a specialized grease lab to get consistency measured, something like ASTM 217, where you actually have a comb penetration test apparatus. And what you would do is the issue with this, of course, is you need a fair amount of grease. And most of the time with our customer base, we're generally getting very small quantities of grease, so we need to do testing in a different manner. But when you're looking at the traditional way of measuring the consistency of a grease, the cone penetration test is you take a aliquot of grease and put it into a little brass holder, and we're dropping a cone from a set height that has a small point on it into the grease. And then after 5 seconds, we measure how deeply that point on the tip of that cone penetrated into the grease. And that millimeter penetration, we then go against our NLGI grade table, as you can see on the right-hand side. So grease is where that cone penetrates significantly into the grease, tend to have a higher consistency, but are a softer grease. The greases where the cone does not penetrate that much have a higher NLGI grade or a lower consistency number. So when we look at the whole range of greases, we have semi-fluid greases starting at a 000 right up to quite hard greases, an NLGI 6. I'm not sure if you're familiar with some of the oil dispensing containers out there, the desk case and oil safe, but we've actually done tests where you can dispense a 000 or a 000 grease out of a large oil safe or a stumpy spout lid. It'll literally pour out of there, albeit not that fast. Kind of has a consistency of honey or molasses. But we contrast that to the very hard greases right up at the other end of that spectrum, NLGI grade of 6. They would be as hard as butter, for instance, cold butter. So in terms of measuring NLGI grade, one thing that we use in our laboratory is the SKF test kit. I mean, SKF is obviously quite well known for bearings and therefore for greases. And they have produced a test kit many years ago that could be used in the field. And we experimented with this for many years and have found that their simple test for doing grease consistency and providing the NLGI grade is quite consistent and quite accurate. So essentially, you're taking a small sample of grease. You have a small plastic disc that has a hole in the center. You put grease in there on a glass cover, little glass dish. You then take the plastic piece off. You put a little aluminum thing around it, put another glass place on top, and put a weight on top. And you let that sit on there for, I believe it's 30 seconds, and remove it. Then you slide it over the glass plates and have a look at how far the grease is spread against this concentric circles that indicate the NLGI grade, and literally read it off of there. So the advantage is you can use a very small sample of grease. I'm going to talk about another advantage of this a little bit later on, about how you can actually use that to look at the contaminants and wear metals and other things that are present in the grease. But at this point, this is certainly one very rapid way of getting the NLGI grade. And I was having this discussion with my internal diagnostics group a few weeks ago. I was showing this presentation to them, and we were talking about what are some of the things that parameters or tests we would use to condemn greases. And it generally, the consistency is the one test that is really a good indication of when something is going dramatically wrong with your grease. So you can see here in the example in the bottom right that we've been trending this grease consistency over a period of many years. And the most recent sample that's on the left side of that spreadsheet is showing a NLGI consistency that's increased by 2.5 NLGI grades, and obviously is indicating some sort of issue. And that's whether uh, the oil itself, and this is from a grease distribution system, so it's possible that there's some type of blockage in the system, or um, they've done a complete grease change out, which seems to be less of a probable cause for this. So the consistency is really a good indication of when that grease has experienced something, whether it's inadvertent mixing with a non-compatible grease, or whether they've been a oil bleed situation where there's no more oil actually left in that grease. Another quick two tests that you can perform on grease is the color and the tackiness. So tackiness, there's a variety of scales that are out there. This is the one we use in this little texture table here. But essentially taking a small sample of the grease and rubbing it between your fingers and then pulling it apart, you can see if that grease is brittle, buttery, long fiber. So when you pull it apart, does it form very long fibers that take a long time to break? Is it resilient? Does it have short fibers, or is it stringy? You'll see the texture actually reported on a number of product data sheets for greases. So a number of the manufacturers do report a texture on there. The second thing is color. This is just a sampling of pictures of those. So when we get the glass plate and we do the consistency, we actually now put that under a microscope, and we do take some photomicrographs. And these are some of the common grease colors you see out there. I mean, there's tans and reds and dark reds and blacks and light grays. It's important to note that grease color isn't an indication of the application that a grease is going to be in. It's really used to help identify the product, and every manufacturer uses different colors for different products. There's no consistency there across manufacturers. But what it does allow you to do is very quickly, again, you can determine if the grease does match what the customer expects is in there. I mean, that's one of the more important things. If we say we're using this specific calcium EP2 grease, then we would, and it's a blue grease, we would expect that grease to be blue. And if the tech data says that it's a long fiber grease, we would expect the texture to remain long fiber. Obviously, as tackiness properties of the grease change, the texture can change, and this can be relevant. Buttery greases should remain buttery. They shouldn't turn into short or long fiber greases. And a long fiber grease should remain a long fiber grease texture. It shouldn't become brittle. Um, that texture is also important if the grease itself starts to become brittle and feel dried out. I mean, obviously that's an indication that we may have an incompatible grease mixed in there, or that we may have no lubricant left in the grease. Another test we can perform quite readily and easily with a small sample of grease is the oil bleed. And again, we refer back to the SKF test kit for this. We take a new sample of grease and we do pretty much the same thing as when we're doing consistency. The same little plastic disc, we put a small aliquot grease in there. This time we're putting it on a piece of Wattman filter paper. That grease then goes in the oven. I believe it's 80 degrees centigrade for 2 hours. And we take a ruler and we measure the amount of oil that bleeds out of the grease. And we measure the diameter of that spot. If it's oblong and not perfectly circular, we'll take 2 measurements and average them. And then we compare the used grease against it. And then we report the percentage increase or decrease in oil bleed in the aged grease. This is an example of greases. These greases were actually from a manufacturer of greases that they were looking to use in nuclear facilities and bearings. And 3 samples were tested radiologically and then sent to us for oil bleed characteristics. And we can see that one of those greases had a rapid decrease in oil bleed diameter as a result of that. So it was 77% less oil bleed than the original grease after radiological exposure. One of the tests that every oil analysis lab employs, of course, is some type of spectroscopy, whether it's Rotrode or ICP in this case, inductively coupled plasma. One thing that we can do with greases, because we love looking at elemental analysis and oil analysis, so we like doing it in grease, is that we can digest these greases or dissolve these greases and then use spectroscopy to get an indication of the metal hydroxides that are present in there, so it can give us an indication of what type of soap is in use. And of course, we can see contaminants and or wear metals. Um, One nice thing about this is that the grease itself, in oil, you have this constant, there's a homeostasis in terms of the wear particles and the wear debris that's present in an oil sample. As the oil is circulating through the system, particles are being generated through abnormal wear conditions or just through the normal oxidation processes that are occurring on the metal surfaces themselves. And that's what a spectrometer is picking up. In a grease, though, obviously those particles tend to stay embedded in the grease and they accumulate. So one of the things that we do see in grease analysis compared to oil analysis is much higher spectroscopic readings for things like iron and chrome and nickel. So in this case, you can see that, I mean, if we were looking at a bearing system with an oil, we would more than in all cases, even when it was an abnormal condition, see 200 ppm or less iron. But in a grease sample, it's not uncommon to see something like this, where you have over 5,000 ppm. As a result, we can actually ratio out the different ferrous alloy content and run it against our internal alloy database. And in this case, not only could we determine that there was excessive wear occurring in this system, but we could actually detect that it was AMS 5510 that was the component that was wearing. So, I mean, obviously this information is very helpful to engineering reliability groups to try and pinpoint where something's going wrong. So looking at consistency and looking at the elemental analysis, when we put this together in a case study, we've been doing a lot of work with greases in turret swivel bearings. This is a slewing bearing that comes off of the actual turret on an FPSO or a floating platform out there in the Atlantic Ocean, looking or drilling for oil. And these bearings are all having grease delivered through a large grease distribution system and header. And the one thing we've obviously noted over time is that the consistency of the grease has been extremely high. And the texture has, which is supposed to be a buttery grease, this OG1 grease from Petro-Canada, was consistently tacky. Um, we did an oil bleed on one of these samples and found that the grease bleed had decreased by up to 60%. So the concern was that the grease itself is not holding up to the saltwater conditions. So there's obviously exposure to seawater, and our concern was that this grease was not staying in these swivel bearings, was in fact being washed out. Um, this the historical results were actually from a different grease, and so the customer decided to change to a grease that was more water resistant in the case of this. One thing we can also look for in the grease, obviously, is water. Water contamination in oils is obviously a problem in a lot of systems. It leads to corrosion, rust or red oxides. It accelerates the degradation of the oil, increases the acid number, shortens the life. And we use a Carl Fisher coulometric oven method for doing water determination in oils. And we can also use that method with some slight modifications for doing grease as well. So it lends itself very well. Then the nice thing about this is that unlike traditional Carl Fisher type method where you're doing what they call a direct injection, where you're putting the sample directly into the titration vessel for measuring water, which we wouldn't really want to do with greases because we're going to foul that reaction vessel and have to clean it after every sample. When you're using the oven method with auto samplers like this, your oil sample or your grease sample is in an individual little vial. The vial is heated by an oven. There's a probe in there where you're literally eluting out the water as vapor into the reaction vessel and then titrating. So some advantages are that you're not having interference from any of the additives that are present in the lubricant in the grease or any of the thickeners that are present in the grease. You should only be measuring water in this case. So the accuracy is better. It also allows us to measure low amounts of water as well as very high amounts of water. And in some cases, some of our greases have very high readings. So when we contrast greases against oils, the typical limits we look for with oils, even in something like an automotive or an off-road application, a wheel hub, we would expect to see less than 0.2% water in an oil. On the other extreme end of that, a lot of steam turbine operations out there with some sort of, say, a centrifugal oil purifier on it, we will have levels at 50 ppm as a target, 0.0005%. So in oils, we're looking at very low levels of water. Greases tend to be somewhat higher. This is a pretty extreme case. So the picture on the top left is of an output device on a continuous digester on a pulp and paper mill, obviously the wet end. And it's difficult to see what you're looking at there because there's so much steam, and if you were looking at this as a video, there'd be water pouring across that bearing. So this was a customer who sent in a samples from 3 different bearings on this output device, and you can see that the grease itself was holding it's the thickener itself that's holding on to water, but we're talking between 17 and 44% water in that grease sample. Because that water itself tends to be, well, it depends on the type. I believe this is a craft digestion process, but you're looking at either acidic or highly caustic water, and as a result, you can see the amount of metal or elemental iron and nickel and chromium that are being created as a result of this water washing through these bearings. The customer was doing some baseline testing on the greases prior to switching out from an extreme pressure grease to a grease that was designed for more water repellent characteristics. I'm still waiting for the subsequent samples now that they've implemented so they went to a calcium-based grease now. Be curious to see what the results look like. One of the, well, I mean, we'd call it a more recent addition to oil condition monitoring testing, but the ruler instrument has been around since I began my career 30 years ago. I think it's just acceptance into laboratories and by the oil manufacturers that took much longer. A lot of times when we're trying to assess the remaining life in an oil, we conduct more expensive, longer running tests like RPVOTs, where we're stressing the oil in the presence of water and a catalyst to see how long it'll last before it begins to heavily oxidize. One thing I like about this test, the ruler, is that it uses something called linear sweep voltammetry, and instead of producing chemistry and oxidation specifically in the oil or the lubricant by using temperature and water and catalysts like copper coils, we're using electricity because essentially oxidation is can be induced by a voltage. So the test not only runs faster, but it actually produces what's called a voltammogram, and we can see the relative amounts of different antioxidants because they oxidize at a different voltage. So the resulting voltammetram from a linear sweep test on an oil and or a grease produces a series of humps, which are the response to the given voltage. And this is a measure of the amount of a specific antioxidants. Most oils contain two antioxidants, something a minic antioxidant and a phenolic. And what you're looking at here on the green is the new unused oil, and that's the aminic and phenolic. And the red is the used sample. Well, in this case, a grease. It's a Kluber-Plex BEM 41-132 grease. So we can actually not only do this test on oils and see the amount, well, the types and amounts of antioxidant remaining, we can also do this on grease. We don't do a great deal of this. We've done, I mean, really more of the grease testing for oil condition monitoring is not really looking at the ability for the grease to get an extended life. It's more about assessing the condition of that grease in operation. And on the oil conditioning monitoring side, really the key thing for us is assessing abnormal or critical wear conditions. And this, I think, is also very applicable in grease applications, even more so than oil. And you'll see through these series of case studies. One of the more rapid tests that we conduct is called, it's a wear particle concentration test. Essentially, it's looking at ferrous and paramagnetic particles that are present in the sample, whether it's oil or grease. This test is called a particle quantifier, or PQ for short, and it's finally received an ASTM method, D8184. So this is a rapid test that's conducted on oils to screen for dramatic changes in the amount of wear material present. So as you may be aware or may not be aware, when you do spectroscopic analysis on oils, which forms the fundamental testing for an oil sample, and the actual wear particles we're measuring are likely in the order of less than 6 microns in size. This is significant because wear particles, by definition, are generally of 15 microns and larger. So the only reason that spectroscopic oil analysis works is because when an abnormal wear mode occurs in a system, it doesn't just produce large abnormal wear particles. It also produces these more benign rubbing wear particles that come off. They're very small. They can be anywhere between a few and 10 microns in size, but they increase in quantity when you have abnormal wear condition. And that's what a spectrometer is looking at. So the spectrometer is really blind to large particles. Some wear modes don't produce small particles when there's an abnormal wear mode. Things like rolling contact fatigues, things that we tend to see in anti-friction bearings and rolling applications. So when it comes to greases, it's even more important to be doing some type of wear particle analysis. It's quite critical in grease applications. So the PQ is a good way to start. When you have a low PQ reading, and subsequently have a high reading on a spectrometer, the ppm levels, it's an indication you have more corrosive type process going on. If you have a very high PQ or a high PQ and a very low iron reading from a spectrometer, it's usually an indication you have an abnormal wear mode. So the PQ is a great rapid screening tool for greases. This is a case study we did in a automotive assembly factory, and of course, there's a lot of Hitachi robots in this. I think they had over 250 robots. They had a very thorough grease program where they were testing these several of the axis joints and bearings on these robots on a monthly basis. And they were using PQ analysis to assess the condition of the bearing. So, I mean, they have spare robots, and it's really not a huge issue to change out a robot. So the reason for the program, though, was that if that robot failed during production, we're talking about $1 million an hour. And if we're taking it 5 hours to replace a robot, then we're looking at $5 million in downtime. So the idea with the program is if we detect a bearing that's got significant abnormal wear condition, then we can schedule that for downtime on Sunday evening and replace that robot and not have any production cost loss. So what we did is we ran the PQ on a number of those grease samples, and then we also did ferrography, analytical ferrography, where we literally extract the wear particles out of the grease, remove the thickener and the oil with a solvent and fix the wear particles, and then look at it under a metallurgical microscope setup. So the two examples we use here, one of them had a low PQ of 35, the other had a significantly higher PQ of 500. The ppm levels from the ICP though were quite similar. But when you did the ferrogram, the low PQ sample, you can see there are some wear particles. Most of them look laminar from rolling contact fatigue, but you can see the significant difference of the higher PQ sample. So this again is really a good indication that doing something like a wear particle concentration test like a PQ is a good way of screening samples for upgrading them to more advanced wear particle analysis testing like analytical ferrography. So with that, I get back to my SK method for doing consistency. So as we spoke of, we take a small sample of the grease, we put it on a small glass cover slip, and then we squeeze it with another glass slip with a calibrated weight to measure consistency in terms of how much the grease spreads out against a concentric ring scale of NLGI grades. But when we're finished with that, we can literally squeeze down that plate and then do photomicrographs of that grease sample. Now that we've probably got about a 1 millimeter path length in between those two pieces of glass. And you look at a couple examples here. So here's a couple of grease samples. Most of these are from crane slewing bearings. Actually, all three of these are. We can see that sample in the middle. It looks good, right? There is some very fine wear particle, a little bit of debris. But the sample on the left, we can see excessive amounts of dirt, scale, bit of wear particle. So right away, we're beginning to wonder if this is a grease sampling issue or whether this is actually an indication of the grease that's present in that bearing. And then the sample on the far right, we can see a very significant wear particle. At the scale we're looking at, that particle is it's humongous. And not only that, it's also extremely angular and quite thick. So this is an indication of a very critical wear process going on in that bearing. So I even kind of balk at calling it a mini ferrogram, but it certainly is a rapid test that we can do to help assess the debris, wear debris, contaminants that are present in the grease. But you've got to use that with some caveats, which we'll see here. So when we combine this little mini ferrogram with ppm levels off an ICP for iron, for instance, with the particle quantifier or the PQ test, here is a series of greases from slew and main bearings in a wind turbine. So very similar applications, actually. They're both very large bearings with intermeshing teeth that rotate, whether it's a crane or whether it's the position of the blades into the wind on a wind turbine. We see a very similar application. And when we look at the iron ppm levels, there's quite a bit of variance, 75 ppm right up to 573 ppm. The PQ variance is also somewhere from, we have 1500 right up to 14,000. So if we were just looking at the iron ppm levels in PQ, we probably would be a little overreactive. But when we look at this mini ferrogram or our consistency grease test that we've now put under a metallurgical microscope, we can see that in almost all cases, these bearings tend to produce very fine wear debris. So in this case, this is just very typical for this type of an application. So, when you start to put the wear particle concentration together with a spectroscopic analysis and with some sort of visual analysis like this mini ferrogram, you get a better indication of what's happening in the grease. Really, though, the definitive test for wear particle analysis is analytical ferrography, and there's a couple methods for producing analytical ferrograms, but they work off the same methodology. Um, we're extracting the wear particles out of the grease thickener or out of the oil sample itself. We're fixing it onto a glass slide, and then we're using a metallurgical microscope to look at the morphology of the wear particles and, of course, any other contaminants that are present in there. The thing about a ferrogram that's unique, depending on whether you use, there's two systems. One is more North American based, the Trico system that was originally developed by the Texas lube refineries many years ago. They produce a particles that travel down the length of a slide. There's also a system developed over in Europe that produces more concentric rings of wear particles. We use the method that produces the cover slip. The slide will have wear particles. The largest will be at the entrance of the slide and the smallest particles at the exit of the slide. Also, the ferrous particles are lined up perpendicular to the magnetic field that is used to pull them and fix them onto the slide. If you see particles that are sort of randomly distributed across the slide, you know they're non-ferrous. You can also use a heating plate to heat treat the slide so that you can determine something about the metallurgy. This is actually oil samples from gearboxes in an automotive assembly plant. This is one gearbox over 18 months, and the wear particle concentration over that period varied significantly. Not only that, through heat treating, we could see that this was a medium alloy steel, and this was a low alloy steel, and this is case hardening steel. We could see a progression of wear patterns from different gear sets in that. So now we apply analytical ferrography to grease. Here's an example. This is a pillow block roller bearing that's from a water pollution control plant, and it's on a series of fans. So the customer was experiencing bearing failures on these fans, and was doing some work with the bearing manufacturer. The bearing manufacturer was sending samples to a lab, and this customer decided they wanted to send their own samples to us. So we do a different test program than the competitive lab. And one of the things that we really rely on is analytical ferrography, as they say. So what's interesting about this is that we were sent a series of blind grease samples. We had a new grease as well. One thing we picked up was that the new grease itself was being contaminated. We were picking up coarse dirt. We were also detecting some level of moisture. We weren't quite sure if that was part of the grease manufacturing process or if that was being introduced, but likely was being introduced by the environment. We talked about grease handling practices, and they open a fresh tube of grease and then go lube all these fan bearings. But if there's grease left over, they were saving that tube. So we were suggesting them that maybe they should dispose and just use a new tube every time. But the wear particles that we were picking up were not really an indication that the contaminant was a significant issue. So what I would expect to see in that case was more cutting wear particles. What was really dramatic is if you look in this center photomicrograph, the one with the green background here from the filter, is that some of these particles were of extreme concern. So again, in ferrography, when you begin to pick up something that's very angular, and in this case, it's quite chunky, when you look at the thickness of the particle, you recognize that there's a more critical wear mode happening. The other ferrogram, we were also picking up some laminar wear. We did a heat treating on this, and we could see that it was a medium alloy steel, and embedded in it was a low alloy steel. So we could tell that there was some boundary lubrication situation here where the grease wasn't performing how it should. But this top sample was a little bit more interesting. And it turns out this was the inner bearing, and the concern here was that in order to generate a particle like this off an anti-friction bearing, whatever the style is, there's got to be some sort of an axial load. And so the concern was that there was improper axial loading as a result of these wear particles. So we had a conference with the customer, and my concern was that this inner bearing might just be cylindrical ball bearings in it, or bearings in it. But it turns out that um, it was the proper bearing for it. They had tapered bearings, and it was bidirectional tapered bearings. So by all means, it was the sort of bearing you would expect. Yet they were still getting abnormal axial load. The customer was kind of surprised because they had done a bearing failure analysis, and it turns out that this is what was occurring. So there was a lot of wear occurring to the one side, I think it was the upper tapered bearing on one point was experiencing a lot of irregular axial load. It could be identified from the failure analysis on the bearing. Not only that, we were seeing some possible false brittling as a result. So you can see this red oxide generation along both the outer and the inner bearing housing itself. This suggests that there's some sort of extra vibration going on. So really, the concern here is there's probably a footing on that fan that's not properly seated anymore, causing excessive vibration and increasing the axial load on that bearing. But it's really shows the power of doing analytical photography, even on a one-off grease sample, for trying to help determine some root cause failure analysis. Another interesting study. This is a little bit more. It's more of it is a study, in fact, rather than looking at something in production. This is a case study from a wind turbine gearbox manufacturer who's produced a new orbit bearing for their gearboxes. What they were doing was testing various loads, speeds, and greases, and sending us samples. What I thought was nice is a lot of these were fairly straightforward, but obviously under whatever load and speed and condition they put this bearing under, it was generate very excessive, not only laminar wear particles were an indication of rolling fatigue, but sliding wear particles as well. Again, we heat treated the slide, and the fact that they rapidly oxidize to a blue color is an indication it's a low alloy steel, although we've got a couple of medium alloy particles in there as well. But it helps the manufacturer identify the type of wear and where the source of the wear is coming from under these types of conditions. The one thing I wanted to show here or highlight is the fact that this is that mini fairgram where we're taking the consistency test and putting it under a microscope afterwards. And you can see that there is going to be situations where you're not even seeing those wear particles. I mean, the actual analytical photography is just a much more superior method. It's just a bit more expensive and requires more time from the analyst to diagnose than just doing this rapid mini fairgram. Another case study that brings a number of these different tests together is some rolling mill bearings in a steel mill slab casting mill. And this is the actual slab casting mill here. And what we're talking about is bearings on the fixed and the free end of the slab caster rollers here. And they, again, we're experiencing some premature failures on the free end bearing on the rollers. So again, they sent us a series of grease samples. I believe we got a new unused grease as well. The exit roll fixed end bearing was showing, as you can see, some very significant wear particles. So again, this is similar to that fan design. We've got a series of tapered rollers meant for not only handling radial but also axial load. So in this case, the suspicion would be that again we're having some axial loading, and we're seeing some pretty severe wear on the tapered rollers as a result of that. But what was more interesting is that on the free end bearing with cylindrical rollers, what we were predominantly picking up was ferrous black oxides. So ferrous black oxides are an indication of insufficient lubrication, probably the best way to say it. Because in order to produce, I mean, when we look at, back up a second here, and we talk about heat treating those slides so that we can determine metallurgy. So obviously low alloy steels are less oxidative resistant in a sense than medium alloy or very high alloy steels or stainless steels. When we take those particles and put them on a very hot plate, um, and bake them, they'll form an oxide layer. And if they form a very small oxide layer, or don't form an oxide layer, then the particle will remain shiny. But as the oxide layer thickens, then the wavelength of light that's being transmitted back or absorbed, and the apparent color, is a longer wavelength light. So obviously blue is a longer wavelength. So when we see blues, we know it's a deeper oxide layer, which means it's lower alloy. To get a black oxide, you need to have a very thick oxide layer. It's absorbing almost all the light. So the particle itself is not reflecting any light. It's an indication of excessive heat. So excessive heat is generally as a result of insufficient lubrication. So for this customer, we were saying, yeah, we see a concern with this free end bearing because we have a feeling that the lubricant itself is not standing up to the temperature in that application. So they need to look at a more high temp grease. And it was good because after speaking to the engineers, they had said that they had already talked about this problem, had determined that what they needed to do was use a high or a better high temp grease on that free end bearing, but they just wanted to confirm it with some grease analysis. And this was exactly the findings. And just to sum up, so in terms of grease analysis, again, you're going to get a sample report, not unlike used oil analysis, obviously, where we look at the standard ppm wear metal levels. We look at the different additive metals that are present, thickener and soap metals, so we can determine if it's matching the baseline of that grease or whether it looks like it's been contaminated with a different grease. We look at contaminants, we look at the grease condition itself, NLGI consistency, texture, color, oil separation, antioxidants. And then if you're doing the wear particle analysis, full ferrographic analysis as well. And as I say, that most of the time the greases we're looking at in my situation tend to be more for troubleshooting. So the recommendations and the discussions tend to be quite involved. All right. So I think we've got about 3 minutes left. Just wondering if we have any specific questions out there.
Okay, thank you very much, Bill. I don't see any question in the chat at this moment. Well, there is one from John. Do you
Well, I
see that,
see.
Bill?
Yeah, I see one
Okay.
up here from Pete Hartfeld, and talking about offshore cranes. We use grease analysis to convince the authorities to extend the period for lifting the crane off a pedestal for slew bearing inspection. I don't know specifically whether customers have done that. I know that we do a lot of work in the marine industry, and obviously they're doing oil condition monitoring in a lot of cases because it allows them to extend, if they can demonstrate that they're doing proper oil condition monitoring on the components, they can extend the life. So I would only assume that also extends out to cranes. The one thing about cranes is that they are extremely critical in these applications. You can't get anything on or off of a platform or an FPSO without a crane. So we know that they're quite critical. I would definitely say that oil condition monitoring is well suited to looking at slew bearings and would definitely be appropriate for extending time out between inspections. Absolutely. And I think the other question was talking about, have you had an opportunity to compare your degradation findings on slow speed applications with ultrasound data? That's an interesting question, actually. So I am not privy to ultrasound, and I'm not sure where John is from, but I know that we were very interested in sensor technology for wind turbines for many years, and we spoke to some people with the American Energy Group, who our engineering firm for a lot of the wind turbine applications down there. And I know that they were looking at ultrasound sensors because they're low cost and could predict certain types of failures in gearboxes and bearings. But I have not put any of that information together. I have seen a lot of greases. A lot of the wind turbine manufacturers now have really ramped up their grease testing programs. So we've seen a lot of grease samples from the likes of Nordex and Vestas. Interestingly enough, I just did about over 120 grease samples for Vestas and didn't see a single wear particle in any of them. The only thing I noticed was that the NLGI grade was decreasing significantly in those applications. But I have seen that both the slew bearing on a crane and the turret bearing, or sorry, a turret bearing and a wind turbine main bearing or pitch bearing seem to produce very similar wear modes. But I haven't looked at lube degradation in those cases. We just haven't had enough customers asking for that type of testing yet. Be a great study. Another question, how much grease is required? So really we can get away with a gram or so. You know, you consider a typical sample, oil sample bottle, it usually contains about 100 mils. We need about, well, we don't need that much oil to do full analysis either. 30, 40 mils would suffice. So for grease, 1 or 2 grams is all that's required. That's what some of the advantages of not doing more of those typical ASTM type testing is you don't require nearly as much grease. A very small sample goes a long way in a commercial lab. What sampling process ensures homogeneous representation? There's a lot of conjecture about that. And I know that there's specific methods in the STM that deal with that. I mean, we're all familiar, or many of us are familiar with Grease Thief and the work that Rich Wurzbach's done with that to develop a sampling device that provides more consistent sampling. We provide a simple kit to customers, anywhere from syringes to straws and tubing to extract greases. One thing I've noticed is that probably the vast majority of grease testing we do is from things like turret and slew and pitch bearings. And the homogeneity is quite surprising because we see a lot of excuse the term, but consistency, not in the NLGI sense, but just in the homogeneity of samples right across customers and across applications that are using those types of bearings. It looks very consistent. You may have a specific application that it's trickier to get a good representative grease sample. A lot of times we're doing failure mode analysis, which is great because they may have opened something up and can actually get grease that's close to the working parts itself. Obviously, if you're pumping grease through a bearing and it's coming out a zerk on the other side and you're taking it there, how representative is going to be is difficult to say. I think one thing that's always important is if we're taking a sample, we take it consistently each time. We don't take it a different way each time. But you're right, it's a little difficult to provide a more homogeneous grease sample than, say, from oil. Turnaround time on testing. Turnaround time, I mean, and most commercial labs are set up for really pushing high volumes of samples through their lab in short order. I mean, the vast majority of our oil samples are going through our lab in less than a day. The grease sample, depending on what you get done, the testing may take 2 or 3 days. If you do the full complement of testing, 4 or 5 days at most. So again, especially where you're doing some type of troubleshooting or failure analysis to root cause analysis, it's not a great deal of time, right?
Okay. Do you have any other questions, Bill?
All right. I don't have a lot of experience. I see a lot of questions coming up with the grease thief. I have not really used that. As I said, what we provide our customers with are the sort of standard spatula, the low-cost syringe with the tubing, and things like a straw for extracting grease. And that seems to be quite suitable. Uh, yeah. So I guess that's it. Again, I want to thank everyone for their participation. I'm really happy to see a good turnout. You know, I'm glad that we've been doing grease testing now for 5 or 6 years, and the program's really matured for us to the point where we feel we're ready to take this to this level of a presentation. We've had a lot of really surprising success with it. I would say it's even more successful than trying to do root cause or failure analysis with oils. It's for whatever reason, the fact that the thickener is holding the particles there for us to examine, but it's really been a useful program for our customers, and we're really looking forward to seeing more samples so we get more case studies.
Okay, thank you, Bill. There are a couple of more questions, but do you want to answer them in next 5 minutes and then we close the session?
Sure.
Okay. Do you see that? I think Martin is asking about the sample digestion on ICP that you said, how it works.
Yeah, so there is an actual ASTM method. So most labs for commercial analysis are doing a simple dilution with a solvent, ASTM 5185. And with greases, though, there's the method is actually calling for microwave digestion or something of that order. We're currently using an acid digestion to dissolve the grease prior to doing analysis. Uh, we we will look into doing digestion. The key thing for me is that what we've done is we've got base greases. So what we want to do is compare the base grease against the used grease. We do tend to get very good levels from our digestion and analysis using standard ICP spectroscopy as opposed to microwave digestion. I think microwave digestion would probably be more important with respect to the actual thickener. I think we would get better elemental response if we were doing the digestion that way. But for the oil condition monitoring side, we've been quite happy with just doing a acid digestion followed by a solvent mix and running standard ICP analysis.
Okay. And I think the next question is about two greases. It says, would you be able to lab comparison of two different type of greases that are supposed to be compatible but result in a catastrophic failure when one was substituted for the other? Is it something that you can do in the lab?
Yeah, it depends what you're really trying to assess. So, you know, grease incompatibility. I've actually done grease samples. Actually, that's a case study I should pull out because I still have this one, and it was a large injection molding machine, a very expensive unit, $5 million machine that was delivered from overseas, was using a specific grease. A year or a year and a half later, the customer was going to reapply grease, spoke to the OEM. The original grease that was in there, the supplier was also in North America, bought the exact same grease, re-greased, and had an incompatibility issue where it actually took the machine out of service. So, it's just it's a significant problem out there. In terms of testing for that, we don't actually do a program where we'll bring in two greases, blend them, work them, and see if they're inconsistent. But part of the oil condition monitoring side is when the grease comes in here and the texture changes to brittle, or when the oil bleed factor is decreased by a significant amount, there's an incompatibility issue.
Okay, so the last two questions, Khalid says, what do you suggest for grease sampling?
Meaning, how do you sample?
Probably, I think,
Or
yes.
what do we suggest for testing? Oh, okay. Yeah. Hey, Khalid, how's it going? um, it depends on the application. Uh, you know, if you're able to, if the application or the grease is exposed and you're able to get at obviously more of the fresh grease closer to the components themselves, be it the 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 bearing itself, that's where you want to get the grease from. If it's a completely self-contained bearing and the only way you're going to be able to get grease is by pumping grease through there and taking what's coming out the other side of the bearing, or the then that's how you're going to have to collect it. As I say, though, having a consistent grease sampling process is going to be key to this. Always sample from the same location. I showed in some of those little mini fairgram examples where the grease had excessive dirt and scale. When we see that, we know that we're probably talking about a grease sampling issue, and that I don't want to really, I want to take those results with a bit of grain of salt and talk to the customer about how they're collecting grease and maybe have some pictures. I think if you have a specific grease sampling concern, you probably want to take a number of pictures and send them along with the sample so that we can assess how relevant that grease sample is. How's that?
Okay, good. And the last question is, what can you tell me about valve greases? Is an analysis of this grease feasible?
Well, any grease analysis is going to be applicable. In terms of valves, though, considering it's not the same sort of. I mean, what are you looking for specifically? What's the issue? What's going on? I think it comes down to what the failure potential is, and the tests I've gone through, whether it can detect those conditions or not. I mean, I don't think we're talking about a wear condition here. Are we talking about a stiction or something of that degree? If that's the case, it could be an increase in consistency, increasing LGI grade that's of concern. Certainly worth a shot. I don't think I've seen a lot of valve greases though.
Okay. Okay, thank you very much. I left my email address on the chat. If there are more questions about this presentation, please email me or email Bill, and we get the answer. I just remind you that this video was recorded. We are going to leave it on the STLE YouTube channel and a link on our website. So you can visit our website, torontostle.com, and you can see all the past webinars and presentation as videos since 2009 there. With that, Bill, do you have anything else to add before we close the session?
Yeah, if you have specific questions, by all means, email me anytime. I love talking about this stuff. So
Okay, good. Thank you, everybody, and have a great day. Thanks. Bye now.
thank you.